human body is a finely tuned machine. All humans are built to the same blueprint of muscle and bone. But we can use them to perform amazingly different tasks. With speed and strength, perfect control, and exquisite balance, our bodies are miracles of design evolution. Witness the power of muscle and bone, next on Body Atlas. Bobby Thatcher is about to take the plunge. He's an Olympic hopeful in rowing, and this early morning workout is just one part of his intense training program. To make the team, Bobby must continually improve his performance. Understanding how his body works gives him the edge he needs to outpace the competition. In his case, knowledge is truly power. Today, he'll be racing the clock as he prepares for upcoming time trials. Rowing is a showcase for the human machine. Bobby's powerful strokes coordinate perfectly with his well-trained muscles. A heat-sensitive camera reveals the inner secrets of the biological engine powering the boat. Muscular pistons connect bone levers that are pivoted at joints and greased with natural lubricants. The muscles are driven by sugar dissolved in the bloodstream. Human power is transferred to an artificial lever. The carbon fiber ore pivots on a steel swivel. Smoothly and efficiently, Bobby's internal fuel supply is converted to the force on the ore blade that drives him on. But to win, Bobby must perfect every aspect of the boat's human engine.
Breathe normally, so 3 breaths.
At an Olympic training laboratory, Bobby tests his lung power. He needs a plentiful supply of oxygen to burn the fuel in his muscles.
Hand fast, hard fast. Keep driving. And in. That's it.
His lung capacity is amazing. He can breathe nearly 2 gallons of air in one breath. Bobby regulates his breathing carefully as he warms up. Gentle exercise increases the blood flow through the body. The muscles tune up to use oxygen more efficiently. The energy Bobby will use is actually already stored in his tissues as a form of sugar called glycogen. As his muscles burn more sugar, his blood carries the extra heat to his skin to be radiated away. The tiny blood vessels in his face dilate quickly to help cool the blood.
Okay, get ready for this piece.
It's time to test Bobby's training. His body is primed, both on the water starting line and on a dry run in the lab.
Set, go!
Go.
Hours in the lab have taught Bobby how to get the best out of his body. He has rehearsed the grueling race under intense scrutiny.
That's it, nice and sharp off, well done.
Bobby must use his limited reserves of energy wisely. Only 1/4 of the chemical energy in his muscles' fuel is turned into useful power. 3/4 is wasted as heat. Human muscle has an efficiency of 25%, the same as a modern automobile engine. But no one can match the huge energy resources of machines. A power graph demonstrates what happens. The first blips show Bobby's initial burst of energy, but his muscles can't keep that pace up for the whole race. He must drop his stroke to a less hectic cruise for the next few minutes. At this slower pace, the human engine is rated at 1/2 horsepower. At peak performance, it can work to 4.5 horsepower. It would take 50 athletes like Bobby to power the average car.
3.5.
Bobby's intensive training is taking his body to new heights. But like any efficient machine, the human body needs a solid framework. A 9-week-old fetus appears to have a full complement of bones, but actually, it's a framework of tough, flexible cartilage. True bones will form around it later. This ingenious bit of evolution allows the baby's skeleton to withstand knocks and its skull to be compressed slightly during birth. The skull plates won't fully connect for 18 months, allowing the baby's brain to grow to full size. Infants are born with 350 bones, 150 more than an adult has. Many of them fuse together during childhood, and by age 25, the average adult is down to 206. This gives us fewer but stronger bones for adult life. Bones are among nature's most perfect creations. They are light but incredibly strong. Ounce for ounce, they can withstand 4 times the weight resisted by reinforced concrete. Underneath our muscular coats, bones shape our bodies. They support us and give our muscles leverage. Our skeleton weighs about 30 pounds. That's less than 20% of our body weight. The shape of each bone is highly specialized, yet the complex structure of the limbs makes them immensely flexible and versatile. The arms are supported by a bony framework across the shoulders, which is only loosely connected to the rest of the skeleton. The shoulder blades are not attached to the rib cage underneath, allowing the arms a wide range of movement. Inside the bones, a mysterious world emerges. 1/3 of a bone's weight is made of living tissue, linked by a microscopic network of blood vessels and nerves. The center of some bones is filled with marrow, which manufactures blood cells. This microscopic architecture lies within many of our bones. Its open structure combines strength with lightness. Bones are not permanent. The minerals that make up the hard part of the bone, calcium and phosphorus, gradually dissolve and are carried away in the bloodstream. New bone is built up from minerals supplied by blood vessels that travel through tiny canals in the bone. As a result, our skeletons are replaced every 2 years. The crystals of new bone are layered to provide strength, similar to the construction of carbon fiber in an ore. Like the ore, the bone levers in the human body must work against a pivot or a joint. Of all the joints in the human body, the knee is the most complex. It must flex while carrying heavy loads. The kneecap allows the muscles to pull strongly around the bent joint. To keep friction to a minimum, the bones are separated by a soft pad. It's filled with a syrupy natural lubricant called synovial fluid. Without their well-oiled joints, our bodies would move as stiffly as robots. Joints and bones work together to amplify the motion of our muscles. The pivot point of the elbow magnifies the movement of the bicep muscle in the upper arm. This wide hand swing requires only a 1-inch contraction of the biceps. But the human hand is probably the most amazing piece of bioengineering. It sets us apart from most of the animal kingdom. The thumb faces the fingertips, providing a strong yet sensitive grip. The 3 longest fingers are operated by muscles in the forearm. Their power is transmitted by long tendons. The fragile finger bones are built for delicate work, not strength, and the joints are correspondingly refined. In contrast, the massive backbone has the weight of the upper body to support. It also provides armor for the spinal cord, the superhighway of nerves that carries messages between the brain and the rest of the body. "31 pairs of nerves fan out from the spinal cord. Towards the base of the backbone is a bundle of separate nerves called the horse's tail. The end portion of the backbone, the coccyx, has no nerves. It's the evolutionary remnant of a tail. This isn't a dinosaur's back. It's actually a human spine. These protrusions anchor the muscles that hold the human backbone together. The 24 individual bones, the vertebrae, are separated by shock-absorbing discs. Our body weight compresses the discs when we stand. We shrink by a fraction of an inch during the day, but we regain it during sleep. Our bony frame is held up by our legs, the strongest bones in the body. They can support up to 1 ton of weight. The foot bones are an exact counterpart to the bones of the hand, but shaped for different purposes. Stubby toes provide springiness. Arched bones spread the weight of the body, which is transmitted through the massive heel bone. The skeleton also provides protection for the heart, the lungs, and other vulnerable organs inside the body. The ribs help to spread the load. The skull is designed like a helmet to protect the brain, but sometimes it meets its match. Deprived of conscious commands, the body muscles give up. But not everything shuts down. The lower brain and spinal cord keep sending messages to muscles that work without our conscious control, powering our breathing and our heartbeat. Even star athletes must rely on the fitness of their involuntary muscles. During his workout, Bobby's heart revs itself up to twice its normal rate. His blood must carry more oxygen to feed his straining muscles. As his glycogen fuel is consumed, his muscles produce carbon dioxide. The blood rushes it back to the lungs to be exhaled. Heat is another waste product that must be eliminated from the body. Bobby's temperature is controlled by sweating and by radiation from his skin. Intensive training allows Bobby to draw more efficiently on the energy reserves stored in his body. Getting his body into shape to compete against the world has taken years of dedication. While other kinds of machines gradually wear out, the human machine can improve with use. Exercise makes the muscles grow in strength, stamina, and size. Ramsford has worked as hard as Bobby to develop his body. He's training for sheer strength and can lift twice his own weight. Even in the average human, muscles make up almost half the body's weight. The outer shape of our bodies is defined by the muscles below the skin. The human body contains 656 different muscles, about 3 muscles for every bone. We don't all look like Ramsford, yet we all have the same number of muscle cells. This number is fixed before we are born. Muscle is made largely of protein. To improve your physique, you need a high-protein diet and program of weight training. But not everyone can achieve this muscle bulk, even with unlimited workouts. Ramsford has inherited the kind of muscles that can be built into a body like this. For feats of balance and agility, it's better to inherit lean-looking muscles with a faster response. Exercise strengthens and conditions these muscles too. It also improves coordination between the muscles and the senses of sight, touch, and balance. Sometimes bulging muscles would be a definite disadvantage. Muscles can generate 40 pounds of force per square inch. If all the muscles in the human body could pool together, they could lift a weight of 25 tons. Outside the realm of voluntary muscles lie 2 other types. The first is heart muscle. It's quite similar to voluntary muscle, but it can't be consciously controlled. The second are smooth muscles, lining the intestines and blood vessels. They, too, are outside our conscious control. All muscles receive instructions from the nervous system. It sends electrical signals down the spinal cord to individual nerves in the muscles. Under the skin, raw muscle is made of thousands or even millions of tiny muscle cells. Each cell is as thin as a hair and up to 2 inches long. The nerve sends an electric shock to the cell's surface. The electrical impulse makes tiny fibers inside the cell contract rhythmically. As they contract, the muscle shortens to 2/3 of its original length. It's fixed in place by tendons, which anchor it to the bone. For light work, the nervous system stimulates only a fraction of the cells in each muscle. If more force is needed, it recruits more cells and fires them more frequently. A muscle's power comes from the chemical attraction between different proteins inside this microscopic fiber. Blood provides a constant flow of oxygen into the muscle and brings fresh supplies of the sugar fuel, glycogen. When a muscle is working, the skin above it warms up several degrees. Heat from the muscles helps keep our normal temperature at 98.6 degrees. Into the lab, Bobby prepares for his final sprint. Are his muscles ready to take him to the limit? He increases his stroke rate. He fills his lungs to maximum capacity, but they can't deliver enough oxygen to his hard-working muscles. To win, he needs an extra boost of energy. His muscles can produce energy without oxygen, but there is a penalty to pay. A waste product called lactic acid builds up in his muscles, causing pain and fatigue.
Seconds to go. Right now, 36.
Bobby's power output hits target as he nears the line. Despite his pain, he has turned in an excellent time. He is one step closer to his Olympic dream. Most of us don't take our bodies to the limit, but pushing the boundaries gives us a tantalizing view into the mysteries of the human machine. It is an amazing vehicle. Its millions of parts pulling together to redefine the limits of the human spirit.